Okay, it's our 3-drum Stirling refractory Spreader-Stoker dump grate boiler. This boiler ran about 250 psi. It's about 1940s technology. It was a low-head 3-drum boiler. It burned Stoker grade coal. Used a Spreader-Stoker and dump grates. The basic furnace was composed of fire brick, about 18-inch thick walls of fire brick. There's water cooling tubes for the refractory so the refractory didn't melt. They were spaced apart. You wanted to cool the refractory, but you also wanted to allow the heat to reflect back into the fire. All the refractory was cooled. You had water wall headers. This one would cool the back wall. This one here would cool the side wall. Then you had one up here that would cool the front wall. All this water come from the mud drum. Was fed down through these. Basic water circuit. Up here you'd separate the steam from the water. I used Chevron dryers and screens. Had a dryer screen on top. The water was separated. You had your feed water dump in here. This is to get the water as cool as you can. Goes down your downcomers. You also have your flue gas coming back up through here. So this is also getting heated. Down in here, any steam bubbles were separated, sent back up these tubes. Then this fed all your water wall headers. Up here, this drum didn't have any internals in it. It was just a drum. It did separation of the water steam just by gravity. The water would come back to your steam drum come over the top down here to the separators. You don't want steam and water mixing down the bottom. Keeps it more of a uniform level, so your feed water control works better. The air circuit, you had a forced draft fan, steam turbine. It blowing underneath your grate, down your ash hopper. The ash hoppers were in 5 sections. Each grate was about 4 feet wide. So each section of grate you could control the airflow on. It fed up through the fire. You have these baffles that direct the flow of flue gas. It goes up through your superheater, back down, and it comes back up to your uptake damper, then out to the stack. The coal feed had a coal bin on top. There's a belt that come up, and the top floor you had a tripper conveyor cart that would dump the coal into the bins. I'd feed down to your hopper. These were Spreader-Stoker. They basically have a paddle that spins fast, and you can throw the coal out. You can adjust the angle and the speed to get the coal bed. The bigger coal would end up down here, and the smaller coal here. The real fine dust would carry up over the furnace. You had a coal outlet valve. You could shut the feed off if you want to take the boiler out of service. Then there's an underbunker conveyor. This would be used if you want to get rid of this coal bin. The boiler had to come offline from a tube leak. You'd shut this and take the coal out of the coal bin, feed another boiler with it, or dump outside. You don't want to leave coal in coal bins very long. After about 6-7 days, you could probably get hot enough to start burning. And if also you had a coal bin fire, thing was smoldering, you can get rid of the coal that way too. You could feed it here and feed another boiler and get rid of the coal bin. Had a low coal switch, just a plate in here. The coal held it down. When you ran out of coal, it'd pop back up, giving you an alarm. The fine coal dust in here would burn or it'd carry over. It'd end up down here as cinder. So there's a little overfire air fan that would push air in, provide overfire air on the back walls and the front walls. This was to hold the flames down and provide a little bit more combustion air. Orifice plates here so you could adjust the airflows and how much cinder return you'd inject back in over the fire. You have your mud drum blowdown valve. These had to be blown down as they're just using softened water, so you'd have dissolved solids build up. If it got more than 350 micromoles, that's kind of what you wanted to run. If it got too high, you get foaming and priming. Foaming is when the water creates a lot of foam and starts carrying this over to your superheater. Priming is when a slug of water actually will go over. The problem is it builds up in the superheater. The water's evaporated and the solids stay behind, so you start plugging up your superheaters. You wreck those. Your outlet, you had your safeties. These are the first safeties to go. Had your non-return off this. Your drums also had safeties. As far as the fuel goes, your Spreader-Stoker would throw the coal out here and you'd burn. You want about a 4 to 8 inch bed of ash on this. It keeps the grates cool. The way these work, there's a air operated cylinder that pull the rod back. The grates would flip up and this bed would drop down to the ash hopper. You had a door here you'd use for raking the beds if you had a pile in here, or if you had a lot of clinker. If there's not enough airflow, you could make a huge clinker and you'd have to break it up, try and drive it through the grates when you're dumping it. When you're done dumping it, the grate closes and you throw coal back on top of it, then it just lights and burns. When this section's burning, then you can jump a section, do another section. So once or twice a shift, you'd have to dump grates, dump the ash. The ash goes down the ash pit, and once a day, they'd use, or to get rid of the ash, use a high pressure water nozzle. It blows in here, then the ash drops out to a trench, then it goes to a pump that pumps out to the ash pit. Those had water sprays on this just to cool the ash. It drops down. Okay, so our section on natural draft. We're dealing with a smokestack. The way they work, if you have 1 square foot of air, that's 12 by 12 inches, 100 feet high. That 1 square foot of air will weigh 7.78 pounds at 50 degrees Fahrenheit at sea level. Now inside of a stack at 500 degrees Fahrenheit, the same square foot would weigh 4.13 pounds. So you have a difference of the 4.13 pounds a square foot. You subtract that from the 7.78 pound square foot, it'll give you a 3.65 pounds square foot difference. So the air in here will weigh 3.65 pounds less than the air out here. So you want to rise. If you take the 3.65 pounds a square foot and divide by 144, this will give you the pounds per square inch, or PSI, pounds per square inch. 1 cubic inch of water weighs 0.0361 pounds. So if you take your PSI, divide by the weight of the water, 0.0361, this will equal 0.70 inches water column draft. So this is how you get your draft reading. So this stack at 500 degrees, 50 degrees outside, 100 foot tall, at sea level, would pull a 0.70 inches water column. If it's 200 foot tall, it'd give you 1.5 inches of water column. So the taller the stack, the more draft you could develop. Stacks, velocity draft, you have the friction of chimney surface and velocity. The more flue gas goes through here, the higher the velocity, you get friction. Just like in a water pipe or anything else, depends on what it's made out of. If it's brick, you're going to have more friction than if it's steel lined. Increase the gas temperature, increase in friction and decrease in density. Hotter gas, to move the same volume, you're going to have higher velocity because the gas is thinner. 1 boiler horsepower equals 60 pounds an hour of gas. This is kind of an old term. Just kind of give you an idea of if you have a certain amount of flows per boiler load. Draft loss also depends on breeching construction, boiler tube passes, resistance to flow. Where the natural draft started having problems was when you added economizers. They dropped the temperature down. Instead of 500, you'd be down to 200. Plus, you have a lot more tubes for resistance. This boiler initially was set up for a natural draft. It had a forced draft fan, steam-driven air fan. Push the air through there. You uptake dampers. These would maintain the draft with a draft controller. And then it'd feed out the stack, as it didn't have any economizer on it. When you added bag houses for emissions, then you had to start adding induced draft fans. The chimney capacity is the weight of the gas, density as well as the velocity. Overloaded chimney, draft drops due to friction. Your chimney can only carry so much flue gas, depends on the diameter, and your draft depends on the height. Even using ID fans, you can develop a lot of draft on a chimney when the fans are shut down doing boiler work. Even doing maintenance work on boilers, if you're in the wind boxes, there's always dust in them. This draft can create a very high winds, make it hard to weld and do repair work. It also helps the ID fans. They are pulling draft still, and it does take some of the load off the ID fans. So basically, once you start adding economizers and emissions, you had to start running ID fans. These require more power to run the plant. Like I say, this boiler here used steam-driven forced draft fan. That exhaust steam was used to heat feed water, run the deaerator. Had your uptake dampers that fed into your stack. Fairly simple design. That's why your stacks have to be so high to develop a certain amount of draft.